Okay, so a couple of announcements just before we begin. Sorry about that. It's a very temperamental projector. So first of all, the final lecture, lecture 10, I sent an announcement to the mailing list, but just in case you didn't catch that, that will take place the morning of the 1st of April. So this isn't an April Fool. So if you thought this mail came to the list and you're thinking, I don't have to wake up that day, there really is going to be a lecture. I appreciate that that is outside the time where classes normally occur. As a result, this is an optional lecture. So it's going to be a lecture on games, case study on classic board games with reinforcement learning. I think it's interesting. It'll pull together a lot of elements of the course, but it's optional. So if you've already booked your time away and you can't attend, then don't worry. It's not going to affect your exam. But if you do have the chance to come along, it should be interesting. And I'll also mention that all of these videos will be made available online very shortly. So if you do miss anything, you can catch up online. Second announcement is the deadline for the assignment. So that will be the following day, April 2nd. So hopefully you guys have made a start on that. If you do have questions, please send them to the mailing list, because if you're wondering about something, probably means 10 other people have the same question, and so it's quite useful just to ping those backwards and forwards on the mailing list to just make sure everything's crystal clear. Okay, so let's get going. So today's lecture is on policy gradient methods. This is a very popular, widely used class of reinforcement learning methods. Again, we're in the part of the class where we talk about things which are actually used in practice to solve interesting, challenging reinforcement learning problems. So just to give an outline of how this is going to pan out, we're going to start off with an introduction where we'll understand roughly what's going on. And then we'll talk about, we'll focus in on policy gradient methods. So what's going on in this class is we're really talking about methods that optimize the policy directly. So instead of working in value functions, as we've considered so far, this is now about working with the policy. How can I see some experience, and from that experience figure out how to change my policy in a direction that makes that policy better? And what we'll do is we'll see a variety of different methods for doing this, which are all based on the simplest principle, if you like, for improving a policy, which is policy gradient. So we adjust the policy in the direction that makes it better. We follow the gradient. We'll consider 3 different ways to do that. We'll start off with a sort of naive but sometimes effective numerical approach by using finite differences. And then we'll move on to see that actually, for many of our reinforcement learning methods, there is an analytic formulation for the policy gradient. So despite what you might think, you can actually just have an agent which follows its trajectory, sees how much reward it gets along the way, but also knows which direction to adjust its policy so as to move it directly in the direction that makes its policy better. And finally, the most practical set of methods which we'll consider are the Actor-Critic policy gradient methods. So these are methods which combine everything from this class with everything from the previous class. So they work with both value functions and with policies and try to get the best of both worlds. Okay. So, introduction. So, last lecture, we had a lecture where we talked about value function approximation. We considered 2 different types of value function approximation. We considered approximating the state value function. So this is the true state value function, which tells us how much reward can I really get in this MDP in expectation if I follow this policy pi. So if I'm in some state S, what's the true expected reward I'll get from that point onwards? Or we had the Q function, which tells us for some state S and some action A, what's the true accumulated reward along some trajectory that I can get from that point onwards taking that action under this policy. So those are the ground truths, and what we did in the last lecture was we approximated those things using a function approximator, like a linear combination of features or a neural network. We tried to estimate this thing. We had some parameterized function, which had parameters w. We basically tried to fit this thing using ideas which are familiar from supervised learning. We tried to fit a function to this ground truth, so we started to understand the shape of how much reward can I get from different parts of the state space and different parts of the action space, respectively. But in that lecture, so last lecture, the policy which we then used when we actually wanted to do control, we didn't represent the policy explicitly. Instead, we just used the value function to pick actions. So once we got our function approximator for Q, that was enough to pick actions because we could just act greedily or perhaps epsilon greedily to pick the action which gets the most Q. So that was a very effective approach to control using function approximation. But it's only one approach to function approximation. And in some sense, more direct or sometimes more natural approach is to directly parameterize the policy, not the value function. So now we're going to have a different function approximator. We're going to have some parameters u. So in the last lecture we had w. So the difference between last lecture and this lecture is like whether it's w or u. And we're going to use these parameters u, and we're going to parameterize the policy now. So we're going to parameterize this distribution. Our policy pi is now going to be something we directly manipulate. So we control these parameters which affect the distribution by which we're picking actions. So think of this, if this was deterministic, which we'll consider later on, this could just be a function. The policy could just be a function. You know, which action do we pick in a given state? And now we learn the parameters which tell us, you know, for each state, which action should I pick? And so again, you could think of this as some arbitrary function approximator, like a neural network, where you plug in your state, and it tells you which action to pick, or a distribution over actions to pick. And so formally, this policy is going to be now a probability distribution over actions that's conditioned both on the state and our parameters. So we're actually defining the probability distribution, and we're tweaking, we're learning how these parameters should change the probabilities by which we pick different actions in different states. And what we're going to do is try and understand how to modify this parameter vector u so as to solve the reinforcement learning problem, so as to maximize the amount of reward that we can get in this environment. And again, what we're going to do in this lecture is we're going to focus on model-free reinforcement learning. So we're really going to focus on how to throw down your agent, throw your robot into some maze, and this thing just wanders around, and just directly from experience, without anyone telling it the dynamics of the environment, it should be able to figure out how to adjust its parameters of its policy so as to get more reward from the environment. And in case it's not clear, the main motivation behind both of these methods is that we want to be able to scale. We want to be able to scale to large, interesting MDPs, large, complicated environments, in which it's not possible to separately for each distinct state say, oh, I'm going to take this action here in this state, and this action here in this state. So we need a function approximator. We need some parameters that sort of specify how, across this state space, we're going to modify these parameters. Apparently I spent too long on that slide. That was the power cable. So while we're waiting for my computer to come back to life, any questions? Hopefully it's, the motivation should be clear. So what we'll start to do now is to understand how we can actually take this parameterized policy with this parameter vector u and start to adjust those parameters so as to get more reward. And the main mechanism that we're going to consider is gradient ascent. In other words, how can we compute the gradient to follow so as to make this policy better? And if we can follow that gradient, we'll strictly be moving uphill in a way that improves our policy. If we know the gradient with respect to the total reward that we're going to get in this MDP, we're just going to follow that gradient in a direction that gets us more reward. And what we're going to do over the next few slides is formalize what that means, if my computer comes back to life, so that we can start to understand how to maximize reward. And we'll consider a few different ways that we can formalize this objective function. So before we do that, I'm going to ask something to you guys while we're waiting, which is, can you think of any advantages or disadvantages of using policy gradients compared to value-based methods? Like, why work with policy-based methods? And you'll think why it might be a better idea to work with policy-based methods than value-based methods. Good.
You need to store fewer things if you're working directly with the policy.
Right, so you might need to store fewer things. So why do you think you might need to store fewer things?
Because you don't have to store the value function or your approximation.
Right, so there are some situations where it's more efficient to represent the value, the policy, than the value function. There might be situations where, imagine you're playing one of these Atari games like Breakout or something, and it might be that the value function is quite complicated. It might be that actually precisely working out how much score you might get from some point onwards might be tricky, but to represent the fact that if the ball is coming down over here, you should always move left, might be a very simple policy to represent. Whereas actually working out precisely that you're going to get 1,714 points if you move left might be a much more complicated function to approximate. So there are cases where a policy can be more compact. So now we've got the slides back, I'm going to come back to this question here. So some other reasons why it might be a good idea to use policy-based reinforcement learning. So maybe the main one you'll see in the literature is that it has better convergence properties, that we saw that there are some cases where value-based methods can oscillate or chatter or even diverge if you do things in the wrong way. Whereas if you just follow the gradient of your policy, these methods tend to be more stable. You're smoothly updating your policy. You don't get these dramatic swings in what action you're going to take, because you just make a little incremental change to your policy and you move in the direction that makes your policy better. And so they tend to have better convergence properties, and indeed if you just directly follow the policy gradient, you're guaranteed to converge at least to a local optimum. Another big one is that these methods are effective in continuous action spaces or high-dimensional action spaces. With a value-based method, you have to work out how to compute the max. And I would say this is probably the number one reason to use policy gradient methods, is they circumvent the requirement to have this max. So if we're doing something like Q-learning, or indeed if we're doing something like SASA, there's always a maximization. I've always been arguing that, well, once we've got Q, all you need to do to pick actions is to maximize over A, and you pick the action with the highest Q, and you're done. You found the best way to behave. But what if that maximization is itself prohibitively expensive? What if you've got a trillion actions or a continuous action space? What do? This is actually quite common. If you've got a robot, it operates in a continuous action space of talks and so forth. If you're trying to, I don't know, solve an internet-based problem where you're trying to create the perfect advert to show to your users, actually creating that advert might have many, many different components that you'd like to move around, and you'd like to make a sequence of adverts that you show that actually maximize your income with that user. This is a vast action space. So what do? Well, you can solve this complicated maximization every step, or you can use policy-based methods where you just adjust the parameters of your policy directly and you never have to solve for this max. It's like you're incrementally starting to understand what the max will be rather than estimating the max directly every step. And the third reason that you might want to consider these policy-based methods is that they can learn stochastic policies. And in the next couple of slides, we'll see why that can sometimes be a good idea. So disadvantages. So the main disadvantage is that naive policy-based reinforcement learning can be slower and higher variance and less efficient than value-based methods. I think the way to think of this is that value-based methods, when you use the max, are extremely aggressive. It's like this max in one step is trying to improve your policy in the direction that absolutely pushes you all the way to what you currently think is the best policy. Whereas policy gradient methods just take a little step in that direction. They smoothly update in that direction, which makes them more stable, but also sometimes less efficient. And sometimes actually computing that step to take, that gradient, if you do it naively, it can be higher variance and slow down the whole algorithm. But we'll see later how to get the best of both worlds by including a value function. And in practice, you may want a value function as well, which can add to the complexity of the algorithm a little bit. And just the flip side of the point which was made earlier, sometimes there are examples like we discussed in Breakout, where a policy can be more compact, but it's also conceivable that there are cases where a value function gives you a very nice compact representation and gives you a more direct way to learn the solution to your MDP. Okay, so let's consider, how can it be the case, why would we ever want to learn a stochastic policy? Ultimately, aren't we just maximizing? Don't we just want the thing which maximizes? Don't we want to maximize our reward? And if we're always maximizing reward, intuitively you might think a deterministic policy should be good enough, because a deterministic policy is always something, you can always find it, maximizing something can be a deterministic process. But there are cases where it's actually desirable to have a stochastic policy, and we'll see two of those now. So the first example is rock, paper, scissors, or Roche-Lambeau, or it has lots of different names depending where you're from and how you play this. But it's just the game where you show paper, scissors, or stone, and scissors beats paper, rock beats scissors, paper beats rock. And so you probably know this, but if you were to just play this deterministically, any deterministic strategy is very easily exploited. If I always play rock, and I start to play against you, you'll very quickly figure out that you should just play paper, and I'll lose every single time. And in fact, the only optimal policy in this domain, in terms of a Nash equilibrium, which is the game-theoretic notion of optimality, the only optimal policy is to play actually uniformly at random. Anything else can be exploited, because if you play one choice more often, your opponent will learn to exploit that. So this is an example where the optimal behavior is actually stochastic. A stochastic policy is necessary. A second example is when we have state aliasing. So this comes up when the Markov property doesn't hold. So we might be in an MDP, but it might be that we lose the Markov property. We get partially observed environment. So if you remember this distinction between fully observed and partially observed, what's going to happen now is we're only going to see certain things about this environment, or equivalently, we're only going to use features which give us incomplete information about where we are in this environment. So consider this little problem here. So as you might guess, getting to this treasure is good, and getting to the skull and crossbones is bad. And this is just a little grid world. You get to move around it, go north, east, south, or west. And the question is, what's the best that you can achieve in this domain? Except we're going to restrict the way that we can create our value functional policy to use the following features. So we're going to consider features which basically tell us they're features of both the state and action. So they're going to be features that say things like, is there a wall to the north of me? Is there a wall to the south of me? In between these squares, by the way, if they're adjacent, there's no wall between them. So this is like, is there an exterior wall? And the other part of the feature is there an exterior wall to the north, and I'm moving to the east? And that would be a feature of my state and action pair. Okay? So we're going to consider features like this. Is there a wall to the north when I'm going east? And we're going to consider all such features, like is there a wall to the west when I'm going south, and all kinds of things like this. And we want to know, what's the best I can do using either value-based or policy-based reinforcement learning. So in each case, we're going to approximate either the value function using these features, and it doesn't matter what the function approximator is. This could be linear, it could be a complicated neural network, it could be your favorite thing. The question is, what's the best that could be done in principle? And we're going to compare it to policy-based reinforcement learning, where we parameterize a policy using some function of these features. And the question is, which will do better? So does anyone have any intuition into this? I'll show it over the next couple of slides, but just have a quick think if you can figure out what's going on. Yeah?
You're not going to be able to tell the difference between those two grey squares with the features.
Right. So the point was that these two grey squares are aliased. There's no way to tell the difference between these two grey squares using the features that you have. Like if you're here and going west, or if you're here and going west, those two things look exactly the same to you. Because you've got a wall to the north, you've got a wall to the south, and you're going west. So your feature vector will be identical, and you can't tell the difference between those two states. So as a result, if you use a deterministic policy, then you have to pick the same action in those two grey states. A deterministic policy, which is parameterized in terms of those two things. And so imagine that you learn a value function now. The value function for these two states has to be the same. And if you act greedily with respect to that value function, you'll either go west all the time, or you'll go east all the time. Okay? And so this greedy idea of generating a deterministic policy, or even a near deterministic policy, would basically lead to the following behavior, which is if you're on this side of the map, you would oscillate backwards and forwards forever if you're using greedy, or for quite a long time if it was epsilon greedy, and you'd never reach the treasure, or take a very long time to reach the treasure. If you use a stochastic policy, then things are much better, because we can optimize our policy so as to choose a policy that goes east or west with 50-50 probability here. So now, if we're in this grey states, we'll just randomly pick a direction, and if we find ourselves over here, well, sometimes we'll go left, but sometimes we'll go back right, and then we'll be pushed down to the treasure. So in just a couple of steps, we're likely to reach the treasure, compared to a value-based method, where if we were to act greedily with respect to our value function, we would end up taking, in certain cases, a very, very long time to reach the treasure, possibly forever. Okay, So the summary of these couple of slides is to say that whenever state aliasing occurs, a stochastic policy can do better than a deterministic policy. So we had a theorem early on in the course which was that there's always a deterministic optimal policy for any MDP. But that's for a Markov decision process where you have, that was in the table lookup case, where we have the perfect state representation. The moment you have state aliasing, so you're partially observed, so if you're in a partially observed Markov decision process, or if you're function approximated, the features that you use limit your view of this world, which is equivalent to being in a partially observed MDP, then it can be optimal to use a stochastic policy, in which case policy search methods can do better than these value-based methods which just act greedily. Okay, so let's talk about how to optimize a policy. So what does it mean to optimize a policy? Well, we need to know what the objective should be. So here's 3 different objective functions we might choose. We want to know how good is this policy. The first choice is, so we're going to consider some parameterized policy with these parameters u, and we want to know essentially what's the best u. So the first case we're going to consider is, if we're in an episodic environment, we're going to consider the starts value. This basically says, if I always start in some state S1, or if I have some distribution over start states S1, what's the total reward that I'll get from that start state onwards? Okay? So this only works if there's this notion of a start state. So if there's a start state, you might say, really, the thing I really care about is I want to find the policy which, when I dump my agent down in the start state, I start my game of Atari and I play it all the way to the end, it gets the most score. Or we could use the average value, and this is something we could do in a continuing environment. So now, in an environment which just goes on forever, there might not be a start state. So now we might want to say, well, let's consider the probability that we're in any state. This is the stationary distribution. This is the probability that we actually end up in any state under our policy pi, times the value from that state onwards. So it's like averaging over the values of all states. So I might be in state 1 and get 10 units of reward from that point onwards, or I might be in state 2 and get 20 units of reward from that point onwards. And so we might average over those and say, well, the objective is maybe 15. Or we might consider another formulation, which is the average reward per time step, which is similar, but we might say, well, what we really care about is just, let's consider some continuing environment. I'm going round and round and round, and all I care about is to make sure that per time step I'm getting the most reward. So we're not summing these rewards over time, we're just saying we're going to take the average of my immediate rewards over the entire distribution of states that I visit. So this is basically saying the objective is there's some probability that I'm in a state, there's some probability I'll take an action from that state under my policy, and this is the immediate reward that I'll get at that step. And what we care about is getting the most reward per time step. That's another way of saying to extracting the most juice from my environment. I get the most reward per time step. This relates to the average reward formulation that was like an extra for lecture 2 that you find in the notes. Okay, so it turns out that, fortunately for us, that exactly the same methods apply to all 3 of these. They turn out to, the policy gradient is essentially the same for all of them. The only thing which differs is the definition of this distribution term here. Like what's the probability that I'm in some state S? And they're just rescalings of each other. So they turn out to basically follow the same gradient direction. And so we don't really need to worry which of these we're following because we end up with the same policy gradient. So now what we're going to consider is trying to optimize one of these objectives. So we're going to pick one of those 3 objectives. And we're going to say what we want to do is to find the u, find the parameters that maximize this objective function. So find the u such that when you drop your AIBO robot down, your AIBO will walk as fast as possible. And so how can we do that? Well, there's lots of familiar approaches to optimization. Hopefully you've come across some of these. Optimization methods are classically divided up into gradient-based methods and gradient-free methods for optimization. So if you don't have access to the gradient, there's some algorithms you could use for optimization, like hill climbing or simplex method, where you've kind of got a triangle that you flip over and over and over as it folds its way down the hill, sometimes called the AIBO or Nelda-Mead. Genetic algorithms, these are all optimization methods that you could throw at a policy search problem and try and find the best policy which maximizes one of these objective functions. But typically, the reason people consider gradient-based methods is if you have access to the gradient, you can almost always get greater efficiency out of your optimization method. And some of the familiar methods for doing this are things like gradient descent, conjugate gradient, quasi-Newton methods. There's another large family of methods that make use of the gradient information to gain greater efficiency, because you know this gradient points you in the direction of greater reward, points you in the direction of how to do better in this MDP, rather than having to blindly try things by trial and error and figure out which of those is the best. So we will focus on gradient descent, the simplest instance of this. Of course, once you understand how to do gradient descent, you should also understand that this can be extended to other methods, for example, second-order methods, like quasi-Newton. All of these things are possible, but I think the ideas are best illustrated and often work most effectively with the simplest case, which with very little computation, you can get a great deal of effective reinforcement learning out of this. We're also going to focus on methods that exploit the sequential structure, by which I mean we're not just going to do blind optimization like a genetic algorithm, where you have to throw your robot down, wait until the end of its lifetime to get one number that pops out of it that says, I achieved X in my lifetime. We would rather break open the trajectory, see that partway through this trajectory it had achieved some sequence of states and rewards, and make use of that sequence of states and rewards to do better than waiting all the way until the end, until this thing dies, before you can actually optimize it. And so we'd like to learn within the lifetime of an agent. Okay, so we'll start with the very simplest version, which is finite difference policy gradient methods. So let's begin by this familiar idea of what policy gradient is. So in the last lecture we considered gradient descent, because we had something like a mean squared error, and we were trying to minimize the error. In this lecture we're going to consider gradient ascent, where we have an objective function, which is something like how much reward can I get out of this system, and we want to make this thing higher. We want to basically ascend our objective function. So we can imagine that there's some surface that says, for any policy parameter, so imagine that these are two different policy parameters, and there's some surface defined by those two different policy parameters, and they might be parameters of how my AIBO walks around, and we're going to adjust those policy parameters in the direction that gets us a faster walk, for example. And this surface has some shape, and the gradient basically points us uphill in the direction of steepest ascent uphill. And so all that says is mathematically what we're going to do is adjust our policy parameters a little bit in the direction of the gradient of this objective function. And the gradient of this objective function is just the vector of partial derivatives. So it's the vector that says, along this direction here, how much progress can I make by adjusting this parameter? Along this other axis here, how much progress can I make? And we just move things in the direction that maximizes our progress and makes the most possible difference in an infinitesimal radius around where I am now. So we're adjusting the parameters to get more juice out of our environment. Okay? So the simplest way, this is the naive approach, the numerical approach. If you had no way to understand what the gradient was, you could just do the following. You could basically look at your objective function and estimate this thing numerically by saying, well, if I just perturb my parameters a little bit, I could perturb them in each dimension. I could say, well, what would happen if I changed my policy parameter along the first axis a little bit? And I would look at the difference between the objective after I perturbed it and the objective before I perturbed it. That would be an estimate of the gradient in that direction. And then we do that for each dimension separately, and that gives us a numerical estimate of the gradient. This is a little bit naive because you need an awful lot. If we're working in high-dimensional space, imagine your policy is a neural network with 1 million parameters. Now you need to do 1 million different evaluations of your policy. You need to perturb it in all those different directions to get an estimate of what the gradient is in that direction. There are techniques that use random directions, like SPSA, which reduce the number of samples you need to take, but they still are very, very noisy. And so it takes an awful lot of computation using these methods to actually even get one estimate of the correct gradient. But nevertheless, it's simple. There's no, this is if you really can just perturb your policy and try again multiple times, you will get something which points you in the correct direction eventually. And so it can work for arbitrary policies, and one big advantage is this works even if you've got some non-differentiable policy. Like someone gives you the program for your robot and tells you, here's some parameters for your program, but we don't know how to differentiate them. You can still adjust it by following this process. So I've been talking about an AIBO, so let's make that concrete. So it turns out that in RoboCup soccer, things have got a little bit better, but I think it's roughly still true that with the AIBO league in particular, this is one of the leagues of RoboCup soccer, they have these little dog robots, the AIBOs, running around trying to score goals against each other. So it's quite a fun competition. But the thing which determines which team wins is basically how fast you can get your AIBO to run. If it can walk faster, you basically are able to just take the ball and move it faster down the field. And so the team with the fastest AIBOs historically has always won. And so it's become an interesting machine learning challenge to make the AIBO gate more efficient and make it run faster. And so the AIBO gate is basically controlled by 12 different real numbers, which are sort of shown in this diagram here. It doesn't really matter what they are. But the goal is to adapt these parameters now. And the first people to do this, Peter Stone et al., they did it by finite difference policy gradient, just like we just described in the last slide. And then what they did was they basically just ran these robots backwards and forwards along this field and measured how long it took them with each gate. It gave them a few walks up and down and measured how long it took. Did that for each of these 12 dimensions separately. And then, so you have to run it up and down to get one dimension, run it up and down again 12 times to get just one gradient update. You adjust your parameters in that direction and iterate this process until your grad students collapse of exhaustion. And so they did this, and let me see if I can pull up some videos. So this is at an early stage before it's really been trained, and I think what the main thing to notice is that it slips a lot. That this thing is really dependent on the ground which it's on, and it tends to slip an awful lot. And over time, it starts to learn something a little bit better. This one. Uh-oh. Oh no, there we go. Let me try that again. I think that was just an artifact. No? But you can see it's learned this much better gate that deals with the slippiness of the surface much better, and it can move much, much faster. So this was just by adjusting the parameters in the direction of the gradient in a very naive, straightforward way, and some limited number of iterations were sufficient to make progress in this domain and actually figure out a reasonable gate. Now, if you move to higher dimensions, these numerical methods tend to collapse. And so what we'll consider for the rest of the class is how to analytically compute the gradient so that you don't have to laboriously compute this gradient separately for each of your dimensions. Okay, so we'll start with the simplest approaches, no value functions yet. That's the Monte-Carlo approaches, and then we'll come back and we'll bring value functions back into the picture. Okay, so we're going to use the following idea, which is we want to compute the policy gradient analytically, and what we're going to assume is that our policy is differentiable. It doesn't actually technically have to be differentiable everywhere, it only has to be differentiable when it's actually picking actions. So if you have some non-differentiability but you're not actually ever picking that action, that's okay. We're also going to assume that we know the gradient of our policy, that we're in control of our policy, something like again, it could be a Gaussian policy or a Softmax policy, we'll see some examples, or a neural network, and we know the gradient of this thing because we've created it. And what we're going to use is a trick called likelihood ratios. And the likelihood ratio trick, I'm just going to put it up in isolation, because what we're going to see is pretty much for the rest of the course, this magic gradient of the log policy term is going to appear. And I think it's useful to understand why this gradient of the log appears, because otherwise you'll just be scratching your head saying, why are we suddenly looking at the log of the policy, not the policy itself. And it basically comes up just from this following likelihood ratio trick, where what we're going to want to do is we want to take the gradient of our policy, we want to understand the policy gradient, and we're going to want to take expectations of that thing. And so the way we do that is we basically note that we can multiply and divide by our policy without changing it, and that this term over here on the right, the gradient of the policy divided by the policy, is equal to the gradient of the log of the policy. Okay? So that's just straightforward calculus. And this term over here is a very familiar quantity from statistics and machine learning. It's sometimes called the score function. But if you were doing something like maximum likelihood learning, this is the term which would come up. If you were just trying to maximize the likelihood of some action A, which someone gave you, you would follow this gradient. This is the thing which maximizes the log likelihood. And so the way to think of this term is this is the thing which tells you how to adjust your policy in a direction that gets more of something. So if you were to tell it the right action and you were doing supervised learning, you would plug in exactly this term for some particular supervised action here, and that would tell you how to get more of that particular action. So this tells you how to adjust your policy in a particular direction to achieve more of something that's good. And so we're going to use that, and what we see now is that by basically rewriting this gradient in this way, we're able to take expectations. Like computing the expectation of this thing is hard, but computing the expectation of this thing is easy because we have this policy here, and this is actually the policy we're following. And so we can take an expectation of this term because this is something we can actually sample from. This is the policy that we're actually following ourselves. So we'll see that in a minute. But just before we do that, let's consider this score function and understand what it looks like for two common examples. So perhaps the simplest example you should have in your mind, which we use for discrete actions, is the Softmax policy. So the Softmax policy is basically something where we want to have some smoothly parameterized policy that tells us how frequently we should choose an action for each of our discrete set of actions. So this is an alternative to something like epsilon greedy, or and the idea is to basically say what we're going to do is we're going to take some features, we're going to form some linear combination of features, for example, and we're going to consider that as like this some kind of value that tells us how much we'd like to take an action. So we've got features of our action in our state, we've got some parameters for those features, and then we weight those features by some weight, and we add it all together, and that tells us how much we desire that particular action A. And then what we do is to actually turn that into a probability, we just exponentiate it, and we normalize. So the idea is that the probability that we actually pick an action is proportional to the exponentiated value that we get when we take a linear combination of these features. So this is called the linear softmax policy. So a softmax in general is a policy that's proportional to some exponentiated value. And you can choose those values to be anything you want. And here we're just parameterizing those values in the simplest possible way by using a linear combination of some parameters with our features. So this is a very straightforward way to parameterize a policy in a discrete domain. So imagine we're doing Atari, and we want to know, should I go left or should I go right? Well, we'd have some features of going left, and we'd have some features corresponding to going right. We would weight each of those, and whichever one scores more highly when we make this weighted sum would get higher probability when we actually come to pick these actions. And now what we're going to try and do is find the gradient of this thing. We want to know, well, how do we adjust this thing so as to get more of the good things? So we need to know the score function, and the score function is very intuitive for this softmax. The score function, the gradient of this locked policy, is just the feature for the action that we actually took minus the average feature for all the actions we might have taken. So it's basically saying, how much more of this feature do I have than usual? And that's the score function. And so what we'll see is when we start to do these kind of policy gradient algorithms, what we'll actually end up doing is saying, if a feature occurs more than usual, that's what this thing is telling us, if it occurs more than usual, and it gets a good reward, then we want to adjust the policy to do more of that thing. Okay, so this is the softmax policy. I just want to give one more example of policy, which is the Gaussian policy. So in a continuous action space, like the AIBO example, the commonest policy to use is a Gaussian policy. And what do we do with a Gaussian policy? Well, we basically just parameterize the mean of this Gaussian, and then you have some randomness around that mean, some variance around that mean, that says most of the time I'm going to take this mean action, that's given by, say, a linear combination of some features. But sometimes I might take some deviation from that mean, and there'll be some variance, like sigma squared, which could also be parameterized. You could have a variable variance. But the simplest case is to say now the action is selected according to some normal distribution with mean mu of s, where this might be a linear combination of our features. Like before, we've got features of our state and some weights for those features, and some variance parameter. So basically we get to pick the mean, and then we just add some noise to that thing to make it stochastic. And so if we were using a Gaussian policy, what would this score function look like? Well, the score function is basically, again, this tells us how to get more of a particular action. And here, again, we have something very similar to the last slide, where this tells us this is the action we actually took. This was our action A. And this is the mean action. This is the mean. So we basically want to know, let's take the action we actually took minus the mean. That tells us how much more than usual we're doing a particular action. Multiplied by the feature. And then we just scale that by the variance. So in both of these cases, the score function takes this form of sort of how much more than usual am I doing something. And that's quite intuitive when we start to look at these policy gradient updates. Okay, so that's just to give some intuition for what these score functions look like. Now let's talk about the actual policy gradient, this analytic policy gradient. And to do this, I'm just going to derive it for the simplest possible case, and homework, if you like, could be to extend this to the full MDP case. We'll talk about what it looks like, but I won't derive it for you. And the special case we're going to consider are one-step MDPs. So what do I mean by one-step MDP? I mean that you start in some start state S. You get to take one step, and you get one reward. It depends on where you were and what action you took. But then the episode terminates immediately. So there's no sequence in this case. It's just a one step, and then you're done. And you get some reward, and the goal is to pick your action so that you maximize that reward. And the right thing to do might depend on the state and the action. So we'll see later this is also called, in a subsequent lecture, as a type of contextual bandit. And so now, if we were to try and solve this, we want to find the policy gradient. We want to understand how to adjust our policy parameters so that no matter what state we're in, we pick an action that's good. We want to adjust our way of picking actions so as to get more rewards. And the way we're going to do that is to start off by picking our objective function. So in this one-step case, all three of those objective functions we talked about become the same, essentially. And so our objective function is just to the expected reward under our policy. So we want to find the parameters which give us the most expected reward. And so we want to find the gradient of this thing and ascend the gradient of this thing, which will give us more expected reward. So if we're thrown into any state and we pick an action according to our policy, we want an expectation that to give us the most reward. And so the way we're going to do that, so let's just expand this out. So this is the expectation over the state that we start in, and this is the expectation over the actions that we pick under our own policy. So this is the expected reward. And now we're just going to plug in the likelihood ratio trick. So we're going to take the gradient of this whole thing. We want to know the gradient that gets us more reward. So the gradient of this whole thing, basically, the only term which depends on u is our policy. So the gradient of this whole thing, we could push the gradient right in to the gradient just of this term here, and expand that using our likelihood ratio trick. So this whole thing, the gradient becomes now the policy multiplied by the gradient of the log policy multiplied by the reward that you get. And so this is, again, now an expectation. That's the whole point of using the likelihood ratio trick. We start with something which is an expectation, you take the gradient, and you recover something which is still an expectation. So this thing is an expectation under our policy. So this is the expectation under the start state, an expectation under the action that we pick of the gradient of the log policy multiplied by the reward. So it's just the expectation of the score times the reward. So after all that, we've basically come back to something very simple, which tells us that if we want to increase our objective function, if we want to get more reward, we just need to move in the direction that's determined by the score times the reward. Okay, and so again, this tells us how to adjust our policy so to get more or less of something, and this tells us whether it was good or bad. So if you have a really big positive reward, you want to move more in the direction that gets more of that thing. If you have a really low negative reward, a really large negative reward, you want to move in the opposite direction to your gradient. Okay? Any questions? Stunned silence. Okay. So, yes?
Can I just ask, this is model 3, right?
Yeah.
And we have the capital R, which means that we know the rewards and everything.
Okay, so notation, this capital R is the random reward, the actual reward that you experience. This curly R is the reward function for the MDP. So we've expanded this in terms of something which actually is described in terms of the dynamics of the true MDP, but we brought it back again to an expectation where we only need to look at the sample reward that the agent actually experiences. So this is completely model free. So model free, what this means is if we want to estimate this expectation, we just take an action from a given state, we compute the gradient of this log policy, which we know because it's our own policy, and we multiply it by the reward that we actually experience. And that gives us a gradient step, and we follow that gradient step. So it's model free. Good question. Okay, so we want to do the same thing in MDPs, multi-step MDPs, not just these one-step things. And to do that, we actually just need to do one trick, which is to replace this instantaneous reward that we had. So we were multiplying the score by the immediate reward. And to do a multi-step MDP, all we need to do is actually replace this immediate reward with the value function, the long-term reward. And that actually turns out to be the true gradient of the policy. And the policy gradient theorem tells us precisely what that means. That's just to formalize that, which is to say that if you start with some policy, then for any of those objective functions we considered earlier, the start state, the average reward, the average value, the policy gradient is basically given by this thing here, which is some expectation over the score function multiplied by the action value function, Q. So it basically tells you, again, how to adjust the policy so to get more or less of that particular action multiplied by how good that particular action was, or that particular action is in expectation. So you want to adjust the policy in the direction that does more of the good things and less of the bad things. And if you were just doing supervised learning and maximum likelihood learning, you'd have something which looked very, very similar, but you just wouldn't have this value function term here. You would just be adjusting things in the direction that made your policy achieve more of the things that your teacher tells you. And so what we have in reinforcement learning is instead of that, we adjust it for all actions. We just have to try those actions and see, well, are they good or bad according to our value function. Okay, so that's the policy gradient theorem. Let's consider the simplest way to actually use that now to make an algorithm. And we call this the Monte-Carlo policy gradient, which is roughly the same as a really old, well-known algorithm called reinforce. And the idea is to update the parameters by stochastic gradient ascent. So we're going to get rid of that expectation now and just do something very practical. And we're going to use the policy gradient theorem. And what we're going to do is just sample that expectation. And the way we're going to sample that expectation is just to say what we wanted to... The term which appeared in the policy gradient theorem was this Q. So let's just sample Q. Let's just estimate Q by using the return as an unbiased sample of this Q. So we're going to be in a state. We're going to start by taking this action, and we're going to see what return we got, and we're going to use that as an estimate of Q. And we're just going to plug that in into our policy gradient to give us an estimate of the direction to move. And so every single episode now, what we're going to do is we're going to say, at each step, we're going to adjust our parameters a little bit in the direction of this score multiplied by the return that we actually got from that point onwards. And so what would that look like in an algorithm? Well, you'd start off, you'd pick some arbitrary parameters, you run your episode, and for that episode, So first of all, you run forward, you generate all of your rewards. This is like a forward view algorithm, so you have to go all the way to the end of the episode, generate your rewards. At the end of that, you know what the return was from each of your steps now. So now you go over each of your steps again, and you say, for each of those steps, we want to adjust our parameters a little bit in the direction of this gradient, the stochastic gradient, which is the score, how to adjust our parameters in the direction that gets us more or less of something, multiplied by this sample return from that step. So that it's as simple as that. It's a very simple algorithm. So this is the most straightforward approach to policy gradient. You just sample returns and you adjust your policy in the direction that gets you more of those returns.
And GT in this case is R?
GT? GT is the sum of the rewards. It's the return. So it's the sum of the rewards from the beginning of the from time step T onwards until the end of the episode. So it's the same definition of return that we've used before. So GT is the return, accumulated rewards from that time step onwards. Okay, so here's a little example. This is using that same Monte-Carlo policy gradient with a particular policy parameterization. And the idea is that you start off with this puck in this world, and this puck is sliding along. There's very low friction in this domain, and you just get to exert a small force on it every time step, which can just slightly perturb its direction. And so if you're not careful, it can really overshoot its target. And then the target is given by this pentagon, which moves around every now and then, and it has to try and reach that target. And so if it gets a reward when it gets close to the target, and it's reset every 30 seconds, and then you just go. You just run trajectories, and you use this Monte-Carlo policy gradient, and you update in the direction of those returns. So you measure your return, you go back over it, and you adjust your policy a little bit in the direction that gets you more of those returns, and then you see how this works. And so there's two things I want you to take away from this. The first is that you get this very nice, smooth learning curve. Value-based reinforcement learning tends to be much more jaggy. You end up with sometimes collapses and sometimes chatters, but you can do very well. The second thing to take away, so it solves this problem very nicely, but the second thing to take away is that the scale here, that, I mean, we're talking, 100 million iterations here to solve this problem. So it's slow. Monte-Carlo policy gradient methods tend to be slow. They're very high variance. They're looking at this complete return of what happened, estimating the gradient from that return and moving in the direction of that estimated gradient. And so the rest of this class is going to be about using similar ideas but making them more efficient. Right? How to take this very nice idea where you get this smooth learning where you adjust the parameters of your policy to solve a problem, but make it more efficient, reduce the variance, make it work better. Okay, and so that's going to bring us to the final family of algorithms, Actor-Critic methods. So just a quick recap. So the main idea is that we've got this high variance estimators of the gradient now. So we had this policy gradient. We plugged in the return to estimate the gradient by taking a sample of our Q values, but that thing's very high variance. Like, it might be that I'm playing, Atari again, and on one particular episode I might get a score of 1,000, and on the next episode I might get a score of 0, and that's just in the randomness of what happens, because, over the course of 10,000 steps there are many, many different random events which might occur. This thing's very noisy. And the main idea of Actor-Critic methods is that instead of using the return to estimate the action value function, we're going to explicitly estimate the action value function using a critic, using a value function approximator. We're going to bring back the ideas from the last lecture, combine value function approximation with our policy methods. So again, we're going to have our true action value function, and we're going to estimate this thing using a function approximator, and then we're going to plug this in to our policy gradient as a substitute for Q pi. So what this means is that we now have two sets of parameters, and that's why these are called Actor-Critic methods. We've got a critic and an actor. And so intuitively, the actor is the thing which is doing things in the world. It contains the policy, it's picking actions, it's actually making the decisions of what to do in the world. That's why it's called the actor. Whereas the critic doesn't actually take any decisions, it's just watching what the actor does and seeing whether that's good or bad, evaluating that thing, saying, oh, those decisions were good, they got a score of 1,000, or they got a score of -1,000. So we're going to combine those two things together, the actor and the critic, and the main idea is now to use an approximate policy gradient instead of the true policy gradient. We're going to adjust the actor, we're going to adjust the policy in the direction which, according to the critic, will get more reward. So the critic's going to say, hey, I think that if you go in this direction, you can actually do better, and then the actor's going to move in the direction of that gradient. And so the way we're going to do that, we're going to take our original policy gradient algorithm, which was an expectation of the score multiplied by the value function. That was our policy gradient theorem. But we've replaced the true action value function with this estimated approximate value function, where we've got our neural network or whatever to estimate this thing. And what we're going to do then is, at each step, we're just going to move a little bit, using stochastic gradient ascent. Every step, we're going to move a little bit in the direction of the score multiplied by a sample from our own function approximator. So the critic is saying, hey, you know, I think this thing is good, or I think this thing is bad, and then we move a little bit in the direction that gets more or less of the things that the critic says are good or bad. Okay? So how do we estimate the action value function? How do we estimate Q? What do we do for the critic? Well, that should be familiar. That's what we did last lecture. We started off with this problem of policy evaluation. We want to know, you know, if I'm following some policy pi, if I'm following this policy pi, we're trying to estimate this Q pi. We're trying to say, how good is that policy? We're not trying to optimize it. We're not trying to build a critic that estimates Q star. We're just trying to say, according to this current behavior, how good is it? How much reward will I get under this current behavior? And then we're going to use that to point us in the direction that will improve our policy. So a way to understand this is we want to say, how good is this current policy pi u for our current parameters u? We want to know how good is that thing. And so we can use everything we've learned so far, Monte-Carlo policy evaluation, temporal difference learning, TD lambda, pick your favorite policy evaluation algorithm, least squares, temporal difference learning, anything you like, throw it into the pot, get an estimate of your action value function, and use that to adjust your actor. So here's a canonical example, just to make things concrete. So let's say we were using a linear value function approximator for our critic. So we're going to estimate Q by using some features of our state and action multiplied by some critic weights, V. So in this class, we're going to use V for the critic parameters, U for the actor parameters, just to keep those separate and distinct from what we did in the last lecture. So we're going to estimate our critic just by using a linear combination of features. And then the critic, we could just update in the usual way, using linear TD0. And the actor, we can update the actor parameters U by policy gradient, score multiplied by what the critic says. So that would look something like this. This is the Q actor critic. So basically what this is saying is that every step of the algorithm, now we don't need to wait until the end of the episode. This is now an online algorithm which we can, every single step, perform an update because we're using TD in our critic. We don't need to wait till the end like we do with Monte-Carlo. So every step of our episode, or every step that the agent experiences, we're going to sample the transition, we're going to see what the reward was, we're going to see where we ended up after that step. We're going to pick an action according to our own policy. We're going to get the TD error between the value before that step and value after that step, just like we did in the previous lectures. Now we're going to update our critic in proportion. Our critic we can update a little bit in the direction of the TD error multiplied by the features. So that was linear TD0, so that's from last lecture. That's how to update our critic in a direction that minimizes the error between what we thought was happening before, what we thought the value was, and what the value ended up being after one step. This is like correcting our errors and making ourselves self-consistent. And we're also going to adjust the actor. We're going to adjust the actor in the direction that gets us more of the things that the critic says are good. So that's the actor-critic idea, using canonical case using linear TD. Okay, any questions so far? I'll just pause there before we're going to start adding more tricks to reduce variance, make these algorithms more efficient. So if you're if you're feeling uncomfortable, now is the time to say, because we're just going to layer more pieces on from here on in. Yes, good.
Sorry. So you have a policy, you get a estimate, and then from that estimate you try to get another policy out. Is that true?
That's right, yeah. So we can think of this as another form of generalized policy iteration, where we start off with a policy, we evaluate that policy using the critic, and then instead of doing greedy policy improvement, we're moving a gradient step in some direction to get a better policy. So it's just like our familiar machinery, where we're making the policy better and better, and every step we're evaluating that policy, moving a little bit up the gradient to find a better policy.
My question is, choosing the first policy, does it differ?
Choosing the first policy, you can pick an arbitrary policy, so you initialize your policy parameters however you want. It could be, typically now we've just got parameters though, we're not using greedy anymore, we've just got some parameters, and those parameters determine our policy. I'm scaring people away from it. Okay, and we're making those policies, we're following the gradient so as to make those policy parameters better, so that our policy gets more and more reward out of the NDP. Okay, so we start off with some policy parameters, that determines our behavior, we want to make that behavior better and better and better. There's no greedy anymore, no epsilon greedy. The policy itself determines how we move around in this environment. These policy parameters. We're always picking actions according to the policy that's determined by these parameters U. So, yeah, one more question.
But if your policy was epsilon greedy over your Q function, do you like fall back to Q then? What happens?
Let me go back to a slide that I kind of skipped at the beginning because the projector was down. This one. Okay. We had this in the introduction, but I think it's worth reiterating. So let's classify our algorithms into either whether we have a value function that we represent, whether we have a policy that we represent, or whether we have both. That's what this Venn diagram represents. If we have a value function, if we represent that value function, we call it value-based. If we have a policy that we represent, we call it policy-based. And if we have both of these things in our algorithm, we'll call it an actor-critic. Okay? And epsilon greedy is something we do when we live in this side of the diagram. Epsilon greedy, we don't actually explicitly represent the policy. Instead, we use a simple trick, which is we say, if we've got the value function, if we've got Q, we're just going to act greedily with respect to Q, and sometimes act randomly. What we're considering now in this lecture is an alternative approach, which is to actually learn directly how to pick actions. We're going to parameterize the policy. So instead of doing greedy or epsilon greedy, we're directly parameterizing the policy. We're deciding how to pick those actions. And we want to figure out, well, if I pick my actions in a particular way, will I get more reward? Will I get less reward? And so we're actually in a different space here altogether, where we're directly parameterizing things. So there's no greedy, there's no epsilon greedy anymore.
But if you parameterize your policy to be like greedy over your Q, over your value function,
if you parameterize it, so that's like an implicit parameterization, which I would say is what we call value-based here. So it's like if we're basically saying our policy is the thing which is acting greedily with respect to my value function, that's purely value-based. We're not explicitly representing the policy.
But does that algorithm still work?
Is there a way to recover
exactly,
like a pure value-based method?
Like
there's a result which says that basically for a particular class of policy gradient algorithms that we'll see shortly, it turns out that if you take the limiting case where you make your step size bigger, so for all of these policy gradient algorithms, there's some step that you take in the direction of the gradient. And you could ask the question, what happens if you take an infinite step in the direction of that gradient? So if we just get back to where we are. So in all of these algorithms, there's some gradient update where we update our parameters a little bit in the direction of our score. And for a certain class of policy gradient algorithms, if you make this thing infinitely large, then it actually takes you to a greedy step. So that's true certainly for natural gradient algorithms, which we'll see later. So the step size is what kind of controls how greedy you are. So think about the softmax policy, okay, this thing where we were exponentiating some score. If you see that like one of these actions appears to be a little bit better than the other, so you had some policy where you were taking this left more often than right, and now you see something where left actually did even better than right, so you saw a good score for this guy. What are you going to do? well, you're going to push yourself a little bit in the direction that makes left even more probable and right less probable. If you make your step size infinite, you'll push the probability of going right all the way down to 0 and the probability of going left all the way up to 1, which is equivalent to acting greedily. So there is a limiting case where you recover kind of greediness, and the step size is what controls the smoothness. So it's certainly true for some algorithms. Yeah, I'll take one more question and then move on.
Sorry, so when you were learning a value function,
Yeah.
you had the development operator being a contraction, and so you knew you were going to get to the optimal value.
Yeah.
Do you have the same thing here? Because you could have suboptimal sort of lows in your...
Okay, this is a really great question. So the question was, if we're using policy gradient methods, do we still have the same guarantees that we'll find a unique global optimum, or could we get trapped in some local optimum? So it turns out that, at least in the case where we're using, so you could consider table lookup representations of policy. So let's consider the table lookup case. In the table lookup case, you can represent your value function by having one value for each state. And if you use the Bellman equation, you get a contraction, you guarantee that you get a global optimum. With policy-based methods, if you just follow the gradient, for example with a softmax, it's known that for the softmax that you also find the global optimum in the table lookup case. So if you have a softmax which is like a separate softmax parameters for each state, you also achieve a local optimum. Now, for the case where you've got some more general function approximator, it's clear that if you've got something like a neural net, neither method will guarantee that you find a global optimum. You can always get trapped in some kind of local optimum. For certain special cases in between, it's unclear, and I think it's an open research question, actually. Right. Okay. So we're still in this space where we've got like this basic principle. We've got this family of actor-critic methods. We've got this family where the actor is basically picking the actions. We've got some policy, we're using that to pick the actions. And we've got some critic, which is basically evaluating those things and saying, whether those actions are good or bad, and then actually the actor moves in the direction suggested by the critic. That's the basic idea of all of these. But what we want to do is to make these things better. So we're considering now some tricks to make this thing better. So the first trick, and perhaps the easiest and best known trick, is to reduce variance using what's called a baseline. So the idea is to subtract some baseline function from the policy gradient. And this can actually be done in a way that doesn't change the direction of ascent. In other words, it changes the variance of our estimator, we can reduce the variance of this thing without changing the expectation. So another way to say that is that what we're going to do is we're going to subtract off some term which looks like this from our policy gradient. So our policy gradient was the score multiplied by the value function. And we're going to subtract off that, we're going to subtract off the score multiplied by some baseline function. And now we're going to choose that baseline function just to reduce the variance, to kind of make this thing mean 0, to make it roughly about the right scale so that we basically, you don't want to end up in situations where one moment you see a reward of 1 million and the next moment you see a reward of 999,000. And you have to kind of adjust in the direction where you're always moving a policy's parameters up, but it's just the relative difference that determines how much up you should make them. It'd be much better to have like +1 or -1, and so this gives us a way to rescale things. And so very briefly, what we see is that if we just expand this out, so our expectation is just, this again is our expectation over states, multiplied by the gradient of our policy, multiplied by the baseline. We can pull the baseline outside of this sum because it doesn't depend on the action. We can pull the gradient outside of this sum, and then we know that our policy sums up to 1. This is a probability distribution, so the probability distribution must sum to 1. So now we have the gradient of 1. Gradient of a constant is always 0. And so we see that this whole term here is actually 0. Right? This whole term that we're adding or subtracting is 0 mean. It's got 0 expectation. Okay? So it's completely legitimate to add or subtract any term of this form. So what that means is that we can basically, whenever we have our value function, so if I go back, whenever we had our value function here, this was our policy gradient theorem, And our policy gradient theorem told us that the direction we really want to move is this score function multiplied by q. But now what this result tells us is that we can add or subtract anything we want from this q. As long as that thing is just a function of state and not a function of action, we can add or subtract anything we want from this so as to control the variance of this whole term here. We want this expectation to be low variance, but we don't want to change the direction of ascent. And so we can do that, and there's a particularly nice choice that we can pick for this thing, which is going to have some nice consequences for us. And the particular baseline which we're going to choose is the state value function. Okay? So what we're going to do is we're going to start off with our q values, our action value function, and what we're going to do is subtract off the state value function. And what we're left with is something called the advantage function. This is something which tells us how much better than usual is it to take action A. So we're going to look at the q value of action A, which tells us how good is it to go left if I'm in a particular state, compared to how good is it to be in that state in general. And that tells us how much better than usual, how much more reward than usual will I get if I take a particular action. And so intuitively, that's just the right quantity to use in our update. So we call this thing D, like the difference, the advantage function. And so what we're going to do is now rewrite our policy gradient theorem in the following way. So this is still the policy gradient theorem. This is still just ground truth. We've just rewritten it by subtracting off a particular baseline function. And so our policy gradient theorem we can rewrite as the expectation of the score multiplied by the advantage function. So again, let's see if we can understand this intuitively. It's basically telling us, this tells us how much better than usual is a particular action A. And this tells us how to adjust our policy so as to achieve that action A. So if this thing is ever positive, if we ever do better than usual using a particular action A, this will tell us how to move in the direction that achieves that gain. If this thing is ever negative, this will move us in the opposite direction, away from the direction that achieves that particular action. So this is always pushing the policy parameters towards situations where you do better than usual. Okay, so that's the advantage function. So again, we're just rewriting the same policy gradient theorem. So how do we estimate this advantage function now? How do we do this in our critic? Well, there's a lot of different ways to do this actually, and I'm just going to suggest a couple of them. So this slide is just to say, well, one way to do this would be to learn both Q and V. So our critic would basically learn Q. It could also learn V using yet another set of parameters. And we would just take the difference between those things as our estimate of the advantage function. So we could basically do that. This becomes more complex in the sense we have more parameters, but it gives us a literal estimate of the advantage function, which we would then plug back in here. So we can plug into this policy gradient theorem here. We plug into this advantage function the difference between our state action value function and our action value function. There's an easier way, and probably a better way, and that's what this second slide is about. So this is probably the most commonly used variant of the Actor-Critic, although it depends who you talk to, and many people use many different variants. And it uses the following idea, which is that the TD error is a sample of the advantage function. So consider the following TD error, this d pi, this delta pi thing here. So if we knew the true value function v pi, then this basically tells us that the TD error is equal to the reward plus the discounted true value at the next state minus the true value in the state I'm in. That's just the definition of this TD error. Now, in expectation, we can take the expectation of this whole thing. We can say, well, what's the expected TD error? And the expected TD error is the expected reward plus discounted value at the next state minus the value of the state I was in. The expectation doesn't affect this thing because there's no random variable in here. S is what we're conditioning on. This term here, the expected reward plus state value at the next state, given S comma A, is precisely the definition of Q. This is just like unrolling our Bellman equation one half step. So Q is equal to the expected state value at the next step. And so this whole thing here basically tells us that the TD error is an unbiased sample. We've basically got our Q minus V now. This is the advantage function. This whole thing tells us that the TD error is an unbiased sample of the advantage function. So if we want to move in the direction of the advantage function, all we need to do is to measure the TD error and move a little bit in the direction of the TD error. In other words, if we ended up, I'm in a state where I think I'm winning a game, I make an action, I find myself in a situation where I'm losing the game, so that generates a TD error. These things were inconsistent. I now have to think, oh, well, I was probably losing the game all along. So you end up with this strong negative TD error that tells you need to reduce your value estimate. And so now what we're going to do is plug in that TD error as an estimate of the advantage to say that whatever I did on that step that generated that TD error, whatever move I made, it was probably a bad idea. So it was something which I was in a situation where I took an action that took me to a situation where I started off thinking I was winning, and I took some move and now discovered that I'm in a situation where I'm losing, so probably that was a bad move. And so that's the intuition here, that we're now going to plug in that TD error as an unbiased sample estimate of the advantage function. And the nice thing about this is that we only need to estimate V in our critic. We don't need to estimate Q, we just need to estimate the state value function. There's no actions that come into it. And what we do is we just plug in, so this would actually be another way to rewrite our policy gradient theorem. Again, this is just a rewriting of the policy gradient theorem. We haven't changed anything. There's no approximation yet. But if we use a critic to estimate V, if we use a V hat now instead of the true V pi, and we use the TD error based on our approximate TD, based on our approximate value function, and we just plug in that estimate of the TD error there, then we end up with something which is a good approximation to this policy gradient theorem. That's a practical algorithm. We estimate V, we generate TD errors using our V, and we move in the direction of those TD errors. And we only need one set of critic parameters, V, to do that. Okay. So just a couple more ideas to throw in for this family of different things that you can try, and then I'll summarize and just bring them all back together. I've got one slide at the end that hopefully is just like a summary where you can come back and say, these are the different things that you can do with Actor-Critic. So this one is really just a reminder of the previous lectures, which is to say, what about this idea of eligibility traces and different timescales? So if you remember from the previous lectures, we've often reused this idea that you don't always want to go all the way to the end of the episode and estimate the return, and neither do you necessarily just want to take one step and bootstrap from the value function after one step, because that's biased. And you often want to trade off the bias and variance between these two things using something like TD lambda. So now we're going to do the same thing with Actor-Critic algorithms, but it turns out that it's quite straightforward to do that. So if you remember from last lecture, we had a choice of things that we could plug in. So this is last lecture. You could plug in when you were updating your value function approximator. You could plug in the return. You could plug in your one-step TD target. You could plug in your lambda return. You can make any of these the target for your updates. And then we also had this idea of eligibility traces, which basically gave a backward view that was equivalent to plugging in this lambda return in the forward view. So hopefully this is starting to become a little bit familiar. If it's not, then go back to the notes, and because it's useful stuff, a key idea. So what we're going to do now is plug in exactly the same idea to our actors. So first of all, we should say that you can do all this with the critic, and sorry, I think some of these should say V rather than W, but you can do all of this with the critic, where you can basically, as I mentioned before, the critic, we can evaluate our policy by any means we like. We can plug in any algorithm we want for our policy evaluator. It could be TD0, it could be Monte-Carlo, it could be TD lambda, least squares, policy evaluation. Any of these are valid. And so we can introduce different timescales onto our critic by choosing a TD lambda or an eligibility trace. But that doesn't affect the actor yet. It doesn't affect the actor. And the question is, can we also get these different timescales on the actor? Can we get information to flow back more efficiently in the actor, so the actor's not just based on the current TD error, but based on something which bootstraps from all different time steps? And the answer is yes. And so, very briefly, all we're going to do is basically we're going to plug in, so this is again our original, this is the true policy gradient theorem. The score multiplied by the value function, or the advantage function, equivalently. And what we're going to see is that there's different things which we can plug in so far. We've seen two different examples. We've seen that we can do the Monte-Carlo policy gradient, which looks something like this, where we plugged in the return. So we used the return multiplied by the score as our estimate, and we subtract off some baseline here. So if we always just subtract off this baseline value function here, you end up with the return minus this value function multiplied by the score. When we used the TD error, we ended up with the one-step target, the TD target, the reward plus the discounted value at the next step, minus our baseline. Okay, so these are different targets. When we use the Monte-Carlo target, we end up plugging in the return. When we use this TD error version, where we're estimating the advantage function using the TD error, we plug in the TD target and subtract off the value function as a baseline. So these are equivalent. These are different ways to estimate our original policy gradient theorem. These are different approximations. And sometimes it's a good idea to do this. This is a high variance, low bias estimator of the policy gradient. And sometimes it's a good idea to do this, where we introduce bias by bootstrapping from our value function, but we dramatically reduce the variance. And again, the goal is to get the best of both worlds, where we want to come up with a gradient estimate which bootstraps from our critic all kinds of different time steps. We don't just want to rely on our critic at this time step to estimate the gradient. We want to use the critic. So we want to be able to say, well, the critic at this time step says I should go this way. The critic at the next time step says I should go this way. So what we really want to do is to combine these together and actually move in some combined direction. And so that's the idea of using eligibility traces. And it's exactly analogous to the way we do it in value-based reinforcement learning, where we compute our TD error, we build up an eligibility trace, and the eligibility trace now basically is an eligibility over our scores. So we basically remember all of the scores that we've seen recently. And so if I had a high score for this particular action in this particular state, we remember that, we bump up our eligibility trace, and then later on when we come to make an update, we move in the direction where the scores have been largest, most recently, and most frequently. So the way to understand this is, the best way to understand this is by analogy with the eligibility traces in the value-based case, where you can literally look at the updates and you can see that wherever you had an eligibility trace in the value-based case, the updates were identical. Like if we were doing value-based reinforcement learning, we would look at, say, our lambda return minus our current value, and we'd have just multiplied directly by the gradient of that value function, not by the score. And so all we need to do is like a search replace. Wherever we had the gradient before, we search replace with the score, and that will actually work and give us a legitimate eligibility trace instead. Okay. So summary of this idea, so we're building up our toolkit of ideas that help us to make Actor-Critic effective in practice. So now we've got a new piece to our toolkit, which is eligibility traces, how to make our actor make use of critics from many different steps all the way into the future. And the nice thing about this approach as well is that unlike Monte-Carlo policy gradient, we can apply this online. We can basically use critics that build up things going far, far into the future, but we can do it online, and we can apply this in incomplete sequences or in situations where the environment is continuing, never stops, or in situations where we're working off policy. Okay. So I think what I'm going to do is I'll talk very briefly about this. So there's a really important question in Actor-Critic algorithms, which is, in some sense, it should be the first question that you ask about Actor-Critic algorithms, which is that we've used this critic, and we just kind of said, let's replace the true critic value with some approximation to that critic value. And we just plugged in that thing and hoped that the gradient that we follow is still correct. In other words, we started off by deriving the policy gradient theorem. We said, this is the true gradient to follow if you really want to improve your policy. And then we substituted in something. We substituted in a critic And we said, okay, well, you should follow what the critic says instead of the true value function. But how do we know that that's valid? How do we know that this really is pushing us in the correct gradient direction and we're not actually following some bogus gradient? And the answer is that, amazingly, if you choose the value function approximation carefully that you use, it's possible to pick a value function approximator that doesn't introduce any bias at all. In other words, despite the fact that we don't have the true value function, and that we're approximating the value function, we can still follow the true gradient. We can be guaranteed to follow the true gradient with our policy updates. And that approach is called compatible function approximation. And compatible function approximation, I won't go into the details of it, but the main idea is to say that the features that we use to have a compatible function approximator, the features that we use are themselves the score function. We basically build up features for our critic where the features are the score of our policy. And if we use that particular type of feature and we use linear combination of those features, then we actually guarantee, according to the theory on this slide and the following slide, which I'll leave to look at afterwards, we can actually guarantee that we don't affect the policy direction, that we actually still follow the true gradient direction if we follow these compatible features. Okay. Now, I know that I'm throwing a lot of ideas at you, and there's a big soup of possible things to follow. I want to throw in one last idea. This is a recent idea. I think it's a useful idea to know about. And it's just this one slide, which is to say that so far we've considered these stochastic policies. We've considered these policies like a Gaussian policy, where we say, I want the mean of my policy to be this thing, and I'm sometimes going to take the actions which are like the mean, and sometimes I'm going to perturb it a little bit by some noise. But this thing can be very, very noisy. Like we're actually, so far, we've been estimating our policy gradients by sampling our own noise. We've basically got a noisy policy and we want to take an expectation over that noise. And it turns out that taking expectations of the gradient of our own noise can be a really bad idea. That this thing is really, really hard to estimate. And in fact, if you start off with like a Gaussian policy and you start to improve this thing over time, and you'd hope it would start to narrow down as you start to figure out how to solve the problem, that as this Gaussian becomes narrower and narrower and narrower, the variance of your estimates actually starts to blow up to infinity. Like it turns out that estimating the policy gradient becomes harder and harder and harder. The noise basically hurts you more and more and more as you get better and better and better at finding the right policy. And that's sort of an unfortunate property of the policy gradient algorithms we've seen so far. Turns out that there's an alternative, and this is something we did last year, which is to work directly with the limiting case. So instead of adding noise into our policy and then trying to narrow this noise down to something which is roughly deterministic, what if we just start off with deterministic policies? So we're going to start off with some deterministic policy, and we're going to adjust the parameters of this policy, this deterministic policy, so as to get us more objective. We're going to follow the same objective functions as we did before. And it turns out that if you just take the limiting case of the policy gradient theorem that we've seen so far, you end up with this very, very simple update, which has a slightly different form to what we've seen so far. But again, you should think of this as just another rewrite. This, again, is exactly equivalent. It's just the limiting case when we actually consider a deterministic function where we've narrowed our noise down to 0. Basically, just got a deterministic function now. We're just picking the mean always. We're never adding any noise in. And it has this particularly nice form where we say all we need to do to follow the gradient, to adjust the parameters of this policy, this should have a u there as well. If we just want to adjust the parameters of this policy to get more objective, all we need to do is to take the gradient of our own Q function. So we look at our critic. Our critic basically tells us, hey, look, if you were, it gives us the gradient that says this is the way that will give you better actions. It says, actually, look, this is how you, this only works for continuous action spaces, by the way, but it basically says, here's the gradient of your value function with respect to your actions. This is how, if you were just to make this action here a little bit higher, you would get more reward. If you were to make this other action a little bit lower, you'd get less reward. So the critic already contains all that information about how to adjust the actions so as to get more or less reward. So that's all there in the gradient of Q. That tells you how to get more reward. Like just move left a little bit more, and you'll get a lot more reward. That's this gradient of Q. And then all you need to do is to work out how to adjust your parameters so as to get more of those actions which the critic is suggesting. And so that's the gradient of the policy here. So this is just the chain rule. It's the chain rule. It says adjust the policy in the direction that gets you more Q. And so that's the deterministic policy gradient theorem. It's very simple, intuitive, and in practice it seems to work a lot better than stochastic policy gradient in situations where we've got continuous action spaces. Scales up much better to high dimensions. Okay. I'm going to skip the natural Actor-Critic. So there's one more approach, which is in the notes, which is the natural Actor-Critic. The natural Actor-Critic is an alternative descent direction, or ascent direction, which has some nice properties. And it turns out it falls out very nicely in the Actor-Critic framework. That's there in the notes. Feel free to refer to it. But I wanted to put up this summary slide before we finish. And this is like a summary of all the different manipulations that we've done to our different Actor-Critic algorithms. So we started off with basically our policy gradient theorem. And what we did was we plugged in different approximations to this thing, where we said, okay, the gradient of our policy, we can get it by taking the score function and multiplying it by the return. We can multiply it by the value function. We can multiply it by the advantage function, so that should be a D. We can multiply it by the TD error. This was another way to estimate the advantage function. We take a sample of the advantage using the TD error. We can use an eligibility trace where we accumulate our scores. Instead of just using the current score, we accumulate an eligibility over all of our scores over many time steps. And we use that eligibility trace instead of just the one current score. And we can use the deterministic Actor-Critic, where we basically move in the direction that gets us more Q. Okay? All of these are essentially different variants of the same idea. They're all different ways, they're different manipulations of trying to say, move the policy in the direction that gets you more value. And then the way that we estimate values in the critic is what varies here. And the way that we make use of this, how we update our policy, is what varies between here and here and here. So the critic can vary, the actor can vary, but essentially they're all doing roughly the same thing. And for each of these cases, we can make a stochastic gradient ascent algorithm, where essentially all we do is we just drop this expectation by sampling the thing which is inside. And in each case, you end up with a very, very straightforward, simple algorithm where all you do is you take a step, or an episode if you're doing the top one, and you look at what happened in that one step only. We now have the gradient of the score for that step. We took an action from some state. We know for that state how to have adjusted our policy so as to have taken that action more often. And we look at whether that step was good or bad according to our critic. If it's good, we push our policy parameters to do that thing more often. So all of these have very simple stochastic updates. And then the critic, we basically use our favorite algorithm, Monte-Carlo, TD, TD lambda. It's the whole family of different approaches that we've considered before in previous lectures. Okay, that's it. Any last questions before we, in the last 30 seconds? Okay, thanks everyone. See you next time.